In the last episode, we saw that several API servers can sit behind one stable endpoint, while etcd keeps the durable cluster state. That solves the single server problem, but it raises another question. If every read still has to reach etcd, what happens when thousands of clients keep asking for the same cluster information? Let us imagine the simplest design. Clients still send their requests to the API server, but the API server forwards every read to etcd. A command asks for pods, a dashboard refreshes, or a controller lists objects, and etcd has to answer every single time. This grows much faster than it first appears. One person may run a command only once, but controllers keep checking the cluster, kubelets keep asking about the pods assigned to them, dashboards refresh, and operators open long-running watches. The same state may be requested again and again by many different readers. Now notice something important. Most of these readers are asking one of two simple questions. What is the latest state I can safely use right now? Or, tell me when that state changes next. They do not need etcd to rebuild the same answer from scratch every time. That is the role of the API server's watch cache. Inside each API server, Kubernetes keeps an in-memory view of commonly used resources. The cache holds the current objects and a short history of recent changes, close to where API reads and watch requests are handled. When the cache starts, it first needs a trustworthy starting point. It reads a snapshot of the resource from etcd. Suppose that snapshot is marked as version 500. The cache now knows both the objects and the exact point in the change history that the snapshot represents. After that initial snapshot, the API server does not keep downloading the full list. It opens a watch from version 500. When a pod is added, changed, or deleted, etcd sends the next event, and the cache updates its local view. Now repeated reads have a much shorter path. A controller asks for pods, a kubelet asks for its assigned pods, or a dashboard refreshes. When the request can safely be served from the cache, the API server answers from its local view instead of asking etcd to return the same objects again. But Kubernetes cannot simply return an old answer and hope for the best. When a request needs the latest consistent state, the API server first makes sure its cache has caught up with etcd. If the cache is behind, it waits for the missing update before replying. The same cache also helps with watches. Instead of every controller opening its own watch directly against etcd, the API server follows the resource once and fans the relevant events out to many API clients. One incoming change can therefore wake up many watchers without becoming many identical etcd watch operations. The watch cache is useful, but it is not a second database. A write still becomes durable in etcd. If an API server restarts, its in-memory cache disappears. The new process simply rebuilds the cache from etcd and starts watching from the new snapshot point. So the cache does not remove etcd from the path completely. Writes still go to etcd. A new cache still needs an initial snapshot. And when the cache cannot prove that it can answer a request safely, the API server can wait or fall back to etcd. The goal is not zero etcd traffic. The goal is to avoid unnecessary repetition. Remember that the cluster may have several API server replicas. Each replica keeps its own watch cache and follows the same etcd state. A request may reach any healthy replica, and that replica can serve many eligible reads from the local cache it has already built. There is one distinction worth keeping in mind. The watch cache we are discussing lives inside the API server. Controllers may also keep their own local caches using informers, but that is a separate layer. The server-side cache protects etcd, while the client-side cache protects the API server from repeated reads. The improvement is now easy to see. Without a cache, repeated reads repeatedly travel to etcd. With the watch cache, etcd remains responsible for durable state and change delivery, while the API server answers many repeated reads and fans out many watches from memory. This is the engineering idea behind the watch cache. Keep the source of truth in one durable place, but move a fresh, recoverable view closer to where repeated decisions are made. That lowers latency, protects the database, and lets the control plane serve far more readers. But the cache now depends on one small piece of information. It must know exactly which change it has already seen, which change comes next, and where a watch should continue after a reconnect. How does Kubernetes give every change its place in that history?